tough crowd this morning. I see evidence of a third.
Yeah, I'm not sure what happened to Wesley. I think he said, well, Vanna's gonna be here. I'm leaving.
Oh no.
But I'm leaving my jacket behind. Right,
I definitely can smell bad after work, but it shouldn't be that offensive, I hope. I hope.
You just had wrong expectations, I guess. Anyway, so for the camera, right now we've got the quiz a week from today on chapter 20 and the master set due the Monday after that. So the only thing I don't really cover in class is the temperature resistances dependence on temperature. And I think it's relatively straightforward if you read it from the book. There's one homework problem in there in the assignment which deals with that. And I think you can handle it. And if not, then presumably someone will ask you a question. And speaking of questions, are there any?
No, after me.
Does it feel like I should be waiting for more people?
I
I was
mean,
gonna say, the only question I had was, how did the test go for everybody, but it feels like we have the answer.
right? Have you had a chance to look at it?
Yeah. I'm not handing them back to I'm partway through it. Some students are still struggling with the difference between vectors and scalars.
Hmm.
There are no tears of joy.
Oh no.
There are no tears of sadness either.
Oh, that's good.
It's more tears of, well, not really tears, it's more of, somehow it's not, I need to do it differently somehow.
Mm-hmm. Whoa.
Hello.
And then there were 3.
What'd you miss, Wesley? You could have been here, you could have had a voice, but knew.
Oh, God, kidding.
All right, and so I think about to start, unless you have a question.
I don't have, you're good.
All right.
Okay.
All right, so we've done the problem with a bunch of resistors in a circuit and a DC power supply. We're now going to make it more complicated. We'll start out with got a battery there, got a resistor there, junction, resistor, junction, another battery, another resistor, and let's never go that way.
That's 3 different batteries?
Yeah. In terms of a practical design, it's rather stupid, but in terms of an exercise in how to do a more complicated circuit analysis, I think it works just fine. So I have 3 batteries. I think of 1 pointing up and 2 pointing down, but the 2 with a positive side down and 1 with a positive side up. Let me throw in some values here. So let's make this 4 volts, 3 volts, 5 volts, 2 ohm resistor, 1 ohm resistor, and 6 ohm resistor.
What about the one in the center?
And what number have I not used yet? 7. 7 ohm resistor. By the way, your next test, the last problem of test 1B is going to be something, different numbers, but it's going to look very much like that. So far, I think the record is around 90% of the class got it right on the test.
Well, that's good. Right.
So considering the few in this class, everybody would have to get it right. Right that. But you can do it. We're about to go over how to solve this, as well as you've been given loads of warning.
And it's recorded. in
Yep.
perpetuity.
We can look back over it.
Right.
Years from now, I'm gonna get it, that somebody's gonna write a comment on the YouTube saying, how many actually did get it?
We should comment on it, there will be there is an exam question in this, so you better watch this video.
All right, so we can't do parallel series resistors like we did in the past to eventually come out with what is the current coming out of the power supply, like we did last time. Well, there are two resistors that are in series here that we could combine. It doesn't really, it saves us about 3 seconds of work. So I typically don't do it. However, which two are actually, could we combine if we wanted to?
Is it the 1 and the 6?
Not the 1 and the 6. There's a junction in between them.
So then the 7 and
Is it-
12? Is it
7 and 5's got,
Is it the 1 and the 7?
not
Or is that
the,
that junction 9?
there's still a junction there.
And it has to be the 1 and the 2 where there's a battery in between but no junction.
Right. But whatever current, for resistors or anything in series, the current flowing across one has to be the current flowing across another. So whatever current I have flowing here has to be the current flowing there, because there's no other place for the current to go. So in series, same current. In parallel, same voltage.
Ooh, could you say that one more time? In series.
In series, same current. In parallel, same voltage.
Thank you.
Now, on a situation like this, you might be able to take a decent guess at the direction that the current's going to flow. The nice thing about it is, it doesn't matter. You pick it. All right, so the two techniques we have are method one. Just want to give one because I don't feel like writing the method out. It's one current per path. Method two is one current per loop, and this is also known as mesh analysis. And just to shake things up, I think we'll start with method one. All right, so when I talk about per path, think about first identify the junctions. I have a junction here and I have a junction there. I have three ways from getting from the top junction to the bottom junction, or three going from the bottom to the top. Whichever way you like to think of it. But I have three paths. I got the left side, the right side, and the middle. What I'm going to do is I'm going to arbitrarily decide which way the current's going to flow. Now, if I guessed wrong, I'm going to get a negative value for the current, and that just means, oh, it went the other way. You don't need to rework it. It's not like some friction problems where you get the negative and you realize, oh, it was sliding the other way, let's redo the problem. With this one, if you get it wrong, you get a negative answer, and your final answer could be expressed as a negative number if you wish. Just make sure you identify direction correctly. We'll talk about that later. Oh, by the way, ultimately the question for this is, what is the current flowing across each resistor? And then typically I have what is the voltage or the potential drop across, and then I pick one of the resistors. Usually either this one or that one. If you look at some of the old tests, the design, it looks a little bit funky. Instead of looking like a rectangle with a line down the middle, it starts out as a rectangle, and then I think it does something like this. That's because I got to the point where when I was working with drawing lines in whichever program I was using, I hit a frustration point, and I thought it's staying like that. And then after a few years, I eventually put it into that form. Now, so what I'm going to do is I'm just going to say this one's going this way. I'm going to label this I sub A. In the middle, I'm gonna say it's going that way. I call that I sub B. And on the right side, I'm going this way. I sub C. Now, I could have chosen the opposite direction for any of them, or all of them, it doesn't matter. But once you establish the direction of the current flow, live with it. Now, because I don't particularly care to write as much, what I'm gonna do is I'm just gonna let, I ran into this trouble the other day. Because A is also for amperes, I'm actually gonna change that A to a D. Just trying to avoid the different meanings for the same letter. What I'm gonna do is I'm gonna use D instead of I sub D, D for I sub D, and C for I sub C. I figure the more subscripts I write, the more apt it is for me to mess it up. All right. So step one, done. We've labeled our currents. Step two, how many unknowns do we have?
Three.
Yeah, so how many equations do we need?
Three.
There we go. One of the equations is the junction equation. Kirchhoff's junction rule says whatever current flows into a junction is the same as the current flowing out. And it actually works for things that aren't junctions either. Whatever flows in, flows out. The one potential exception at this point, you might think of a capacitor, because I have charge flowing onto one plate here, and then I have the same charge flowing off there, but what about this gap here? What's going on there? Does that violate Kirchhoff's rule? It actually doesn't, but we need to cover a couple more chapters before we actually resolve that issue. So, top junction, bottom junction, it does not matter. If I had, if I had more up here, then we'd have to do some multiple junctions, but for here, I have the same three currents involved in both junctions. I usually pick the top one for no particular reason other than habit. The current flowing in, well, which current do I have flowing into it?
B. B?
Flowing into the top one?
It looks like it's passing through it and then turns downward. Is that not what you meant?
These are two different currents here.
Oh, right. Okay, so
So you're saying which is flowing into what?
Which flowing into the top junction?
it would be D.
Yeah, D.
D. I heard B when you talked before.
That is what I said. I
Okay.
was confused.
And then what's flowing out?
B.
C.
B and C.
Yep.
B or C.
Right.
So our first equation done right there.
That's B.
That's the easy one.
Here.
The next one, or the next two, gotta be really careful with the signs. There are so many places to mess up a sign. And just be careful. All right, so the next two equations are gonna come from the loop rule, the voltage rule. The fact that I'm gonna start someplace, I'm gonna work my way around and end up back where I started so that my total voltage is 0. That's Kirchhoff's voltage rule, or loop rule. Now, personally, I like the first thing that I write for the equation to be a positive. Not every student does that. Some students just do some very bizarre backward stuff. Then that's fine, as long as they keep it straight in their head. So what I'm gonna do is I'm gonna start here, and I'm gonna go around this left loop. Now, there's three loops I have choices here. I have my left loop, I have a right loop, and then I have the entire one. They are not independent of each other, so I can't pick all three. If I pick all three and I try to work with that, if I don't make any mistakes, I should end up with something incredibly revealing like 0 equals 0. Because they're not independent of each other, you won't actually be able to solve for anything. So that's why we need that as one of our equations, and then we'll have two other ones based upon 2 of the 3 loops.
So we can't write another equation yet until we go through the individual loops. Like you can't just write B plus C equals D for the bottom junction.
Right, it's the same thing, mathematically.
Oh, right, okay. Yep, got it.
All right. Other questions at this point before we tackle this?
Huh.
All right. So I'm starting here, I'm gonna work my way around. Now, I could go counterclockwise, absolutely nothing wrong with that. I'm just going clockwise this time, out of habit. Mainly because I usually start over on this battery, and since this one has the positive side up, I'm starting here, working my way around. If I had that battery flipped around, I probably would start here and go around the other way. It's one of my eccentricities, one of my many. So as I go across this battery in this direction, am I going from negative to positive or positive to negative?
Negative to positive.
Yep. So I gain potential. Matter of fact, I gain 4 volts. Now, I'm not gonna write the units down, just the 4. I know it's volts. Then I come over here and I go across my 1 ohm resistor. I'm going with the current, and when you go with the current, you lose potential. Think back to the circuits we did where we just had a battery and a resistor. When we went with the current, we gained going across the battery, we lost going across the resistor so that we could end up back at 0. So I'm gonna lose potential going across this, minus 1D. So this is Ohm's law. Remember that my change of potential across the resistor is I times R. My current is what I'm labeling as D, and my resistance is 1. So this D is not a unit, it's a variable. All right, come to this junction right here, and then I'm cruising down this way, and I'm going across my 7 ohm resistor. I'm going in the same direction as the current I defined, because I said V was going down. So minus 7V. I go across the 3 volt battery, because again, I'm still going in this direction here. When I go across the 3 volt battery, am I gaining potential or losing potential?
Gaining.
Plus 3. And then I'm heading back to where I started. I go across my 2 ohm resistor in the direction of my current, minus 2D, and then I'm back where I started, equals 0. Questions to hear?
You chose D and B for your variables because that's the loop you're in?
Yes.
Okay.
Yeah, it's whatever, because once I have to define the currents first. Once I've defined the currents, then I'm stuck with it. So whenever I do a loop across the 7 ohm resistor, 7B is gonna show up. All right, so the next one, I now can take the right side or the entire thing. It doesn't matter which one I pick. I am going to take the right side, unless somebody has a strong preference to do the whole thing. Yeah, let's do the right side. I'm gonna start here, and I'm gonna go clockwise. Why am I going clockwise? Because I'm starting next to this one, and I like the first number to be positive. It's one of my things. So someone want to take a shot at how my second equation starts?
5.
Okay, cruising along, hit here, and then start moving up the middle. What's next?
You're gonna lose potential 3 volts.
Okay. And then,
Since you're going against the current, we should be gaining here, so it should be plus 7B.
and then,
Plus 6, right? It's plus 6?
Y plus.
Is it minus
I think
6?
minus, right?
Yeah.
Y minus 6.
Because you're going with the current this time.
So what am I just writing down? I can't just write down minus 6.
minus 6c.
Yeah. And then I'm back where I started. I now have 3 equations, 3 unknowns. If I added these 2 equations together, just straight up, nothing manipulated, just add them up, I will end up with the equation if I had done the entire circuit. So that's why the 3 are not independent of each other. I can derive the 3rd one from the whichever other 2 I have. All right, at this point, the first part of the physics is done. We now have a math section, and then we have some physics at the end. So let's start doing the math piece. 3 equations, 3 unknowns. First, I'm going to clean it up. So I have D equals B plus C, nothing to clean up there. Down here, I'm combining like things. I got 4 plus 3. Got negative 1D minus 2D. Minus 7D equals 0. And then my last one down there, I've got 2 plus 7B minus 6C equals 0. And then I do a quick check to see if I made a careless error, and also give a pause for anyone else who wants to point out a careless error I just made. Okay. Personally, when I'm solving this, I do a mixture of different methods from the math piece of it. For instance, I might do substitution to solve for one of them, and then solve equations simultaneously for another, and maybe do Cramer's rule for the third. Or if you're comfortable with doing matrix manipulation, you can find inverse matrix. You can set it up as a product of matrices, do an inverse matrix, and so forth. There are lots of techniques. If you are incredibly gifted, you plot this in 3D and figure out where they cross. I guess calculators potentially do that now, I don't know.